Let us see here. For example, the first element. We have the first node, the second node, and the third node. Okay, so the first node here. In this first node, and this one is free. Free means what? The traction is prescribed and equal to 0. So the first one, the traction in one direction, and in the second direction, and in the third direction. Where is the first direction? The first direction is this one. This one is the first direction. This one is the rotation in the second direction, and this one is the shear in the third direction. The three here, we don't have bending moment in one direction, and bending moment or torsion moment in the second direction, and any shear in the third direction. The second node is the same. Okay? The third node is different, because here we fix the displacement here. So the displacement is fixed here. So as far as the displacement is fixed here, that means we have 0 displacement. So we do expect here, as far as the displacement is fixed, that means we have fixed support. So we expect that we will receive traction in this direction, traction in the first moment direction, and the second moment direction, and in the vertical shear direction. When we move to the second element, I will put it by red. These two nodes should be the same in displacement. Because of that, we need to force this one to have 0 displacement. Otherwise, we will have a gap, we will have crack. Okay? Otherwise, we will have crack. Okay? This is very important. So this node is fixed in this element, and this fixed in this element. If you don't want to fix this node in the horizontal element here, we need to use discontinuous element. Okay? So these two should be the same. And the second node here is zeros. The third node is zeros also. These two nodes, this one and this one. And the same, this node should be the same on the horizontal element at the bottom here. So this line should be zeros also, to ensure the displacement compatibility between this at this corner. Okay? Until we reach all of the other are zeros. Where is the load? We don't have external traction. Our load here, remember, our load here is this load, is the uniform load as domain load over the area of the plate. All of the area of the plate, it has -1 ton per meter square. So actually, what we want now here, we want to check our results. Actually, we want to check our result. What kind of result we want to check? We want to check our result for displacement. We want to check our result for tractions to ensure equilibrium. Now we have equilibrium. Sigma, the forces in the third direction, is equal to 0. Sigma, the moments about x1 equal to 0. Sigma, the moment about x2 equal to 0. Okay? So this is the input file. How to write the input file? You will have this program on the drive. I will place it on the drive. You can try it by yourself. Okay? And this is the output is the same like the output you can see here is version 1 of the PLPAK. Actually, this was the original. It was written in 1995, something like this. Okay? And this is, it gives you the same output, like the input is the same, like the one that for 2D elasticity. And at the end of the day, you will have, this is your result. Your result here, it has the first one. It gives you the boundary displacement. Where is it? This value is the boundary displacement. So you have 3 displacements. This is U1, this is U2, and this is U3. Remember, U1 and U2 are rotation. U1 about this direction. Remember, we have, this is x2, and this is, we have x1, and we have x3. And our plate is like this. It's fixed here, and it has vertical load here, 1 ton per meter square, and fixed from this side. Okay, so here is, this is U1, the rotation about x2, and this is the positive direction for U2, and this is the positive direction for U3, which is the deflection of the plate. So this is the values you have, and here's the traction. It gives you the traction for the first element, the second element, the third element. So this is the first node of the second node and third node for each element. For example, something like this. So this is first node and second node. This is the first node, the second node, the third node. And in the second element here, this is the first node for the second element, and this is the second node for the second element, and this is the third node for the third element. And it gives you another thing. It's called boundary element reactions. Boundary element reactions, I integrate over the element for the traction, Gx, dx. This is the total traction on the each element. For each element, you give you P1, P2, P3, which is the integral of the traction. And I put one internal point here at the middle. If you remember in the input file, where is the input file? Here is the last one, we didn't talk about it. This is the internal point. I give one internal point as the coordinate is 2, and 2 is the one in the middle here. So it gave me, at the end of the day, it gave me the moment mx and mxy and my and qx and qy. Remember, we have, it gives us the output for the plates is three moment stress resultant, mxx and mxy and myy, and the two shear stress resultant, qx and qy. Okay, I'm going to check manual my result. I'm going to check manual my result. The first thing I want to check the deflection at node 8. I want to check the deflection at this point. Okay, the deflection at this point at node number 8, this one. Can you remember? Can you see this one? This number. I want to check this number. How can I check this number? I know you don't have background in mechanics, but the idea is very, very simple. We use virtual work. What I did here in the previous slide, I'm going to show how can I did. I use virtual work to check the deflection. The idea is very simple. If you have beam like this, under distributed load, so we draw the bending moment diagram for this distributed load. It's very simple. The bending moment diagram, this one is W L square over 2, and this one you have here parabola. This is from mechanics. It is equal to W L square over 8. This is the bending moment diagram M naught, and you can put just virtual load here, 1 ton. This is virtual load. You will get another virtual bending moment, which is M1. Okay, this one is L, 1 times L direct of the beam, the length of the beam. You can say 1 times the deflection. 1 times the deflection here is delta is the deflection here. 1 times the deflection equal to integral over the beam from 0 to L, M naught M1 over EI times ds or dx. If you integrate these two together, we can integrate two figures. It's very simple. You can integrate if you have two lines like this. It's very, very simple. You can prove it. This is very easy. This one A and B, and this is C and D. If you integrate these two together, it is L over 6 times A times D plus C. Sorry. It is A times C plus B times D plus A times D plus C times B. Okay, this is the integral. You can prove it. You can prove it. It's not a problem. If you get the equation of this line and the equation of this line and integrate these two together, you will get this result. Or you can get the area of any shape multiplied by where the CG of the area comes down. You compute the area times this point, x bar, for example, not x bar. So you can use this one or you can use this one. Once you do that, this is exactly what I did here. EI is the moment of inertia for this section. So I computed the deflection using the same. This is, I use the area here. I made a mistake here. Actually, this is, you have two here. I'm sorry. Okay. And this is the area of the parabola times this one. You look at back at about the calculation. Is straightforward. You will get it from calculation is 0.0228, and from the computation using only one boundary element is 0.023. So actually you get something like 2 digits or something using only one boundary element. If you repeat the same problem using 2 boundary elements or something like this, you will get it direct. And this is analytical value. This is the analytical value. Okay.